Hello, I'm Bill Johnson. I'm an SRE for Azure at Microsoft, and I contribute to some of Microsoft's sustainability efforts and commitments that they've made. I want to first say thank you to USENIX and the organizers of LISA here for having me to the conference and being able to talk about this very, very important topic. My real world counterpart is going to be doing some, light heckling of myself on the side and answering questions in the Slack as we go. So feel free to ask questions there, and I'll do what I can. If you're watching this later on in a video, then all my contact info will be at the end, and you can feel free to reach out to me there. So today I'm going to be talking about sustainable software engineering, and particularly how software engineering relates to the planet. And then I want to connect that to SREs, because I feel that SREs are in a perfect spot to both drive sustainability within their team, but also within their companies, and then to the larger world overall. So normally when you start talking about the environment and climate change, it turns in very doom and gloom, and rightfully so, because it's very serious, and we're not in a great spot. So I actually like to approach this a little bit differently, in the sense that I like to view it as our planet has an SLO. That SLO is we need to stay within 1.5 degrees Celsius average global temperature across the whole world, compared to our 20th century average. So in short, we're not doing very well at all. Measurements and data sources, they vary, but we're roughly about 1 degree above as of 2020. We're projected to kind of breach this 1.5 degree mark somewhere in the next 4 to 7 years. Again, measurements, they vary a little bit, but the consensus seems to be falling within 4 to 7 years. And then in fact, if you actually look at the top 7 all-time warmest years since we started taking measurements, they're all in the last 7 years. So we're definitely on the wrong end of the trend here. But SREs, we're infinitely curious. And so let's dive in and kind of see what's causing this SLO to rise. So in short, greenhouse gases are causing this. They're causing the temperatures to go up. And if you look at greenhouse gases in this chart here, you've got your F gases, which are the HFCs, CFCs, hydrofluorocarbons, and they are essentially what's emitted from the refrigerants and coolants like air conditioners, those types of things. It's a relatively small amount. You've got some nitrous oxide, which is more or less naturally in the air, some methane, which is a little bit natural, but also comes from agriculture and cow burps and those types of things, as well as burning off some gases. But the vast majority, 76% in this chart, let's call it 3/4, is from carbon dioxide, is from CO2. And so what does that consist of, those 76%? Well, if we break that down even more, we see that roughly half of that is all due to both electricity and agriculture, or food production, essentially. And so, sure, we can probably do some stuff on the food side for our jobs, and maybe we call 2 pizza teams, 10 Impossible Burger teams, or something like that. But all of our laptops, all of our desktops, all of our servers, all of our phones, all of our Raspberry Pis, whatever, they all need electricity to run. So this is something that's very, very in tune with what we have and connected to what we're doing every single day as engineers. So taking all that together, electricity is 20% of our total global greenhouse gas emissions. And that equates to roughly 8.2 or almost 8.3 gigatons of carbon. It's the biggest factor in greenhouse gases is carbon. And the biggest factor in carbon is electricity. And so if we reduce electricity, we can reduce carbon. I'm focusing on carbon here pretty heavily, and I'll continue to do that through the talk, but I want to touch on one point. There's a thought that, if it's all just carbon and it's all electricity based, we'll just move to renewable energy. Everything will be solar. Eventually we'll be fine. No harm, no foul. Let's go on with our daily lives. And yes, please, we need to continue to move to renewable energy, but it's not just carbon at the end of the day. There's all kinds of other things that come into this. And most notably, one of them is water. And so water soaks up carbon from the atmosphere into the water itself, and it acidifies the oceans. It acidifies the lakes. That ends up killing the animals, the fish, the mammals in the ocean. It ends up killing plants that are in the ocean. It ends up bleaching coral in the ocean. It has tons of ramifications from there. Additionally, with water, the way that we typically will cool data centers or server racks is through water use, and water is getting more and more difficult to both get and acquire, and also more expensive to acquire it. So those costs are also going up. And then there's another component here of waste, and specifically e-waste, electronic waste, is a huge deal. So, many of us have had, multiple iPhones or Androids. The first Android and iPhone came out a little over 10 years ago. Where are most of those phones now? Probably in a landfill somewhere. And that's, CPU components, phones, laptops, about 3 years, maybe 4 years if you're lucky on a laptop, is how long it lasts. And then it typically gets, thrown away, or hopefully some of the parts are recycled into other pieces. Apple alone, just with iPhone, sells about 200 million iPhones a year. And so that really adds up quickly. So carbon is by no means the only issue, but it's what we're going to focus on today. And specifically, let's get back to SREs in particular. So why should SREs care about this problem at all? Well, first and foremost, I love this kind of quote from a tweet from Jez Humble. That's it really focuses on systems thinking, that as software engineers you have to take the whole system into account. You have to connect to the larger world with the work that you're doing. And so this is paramount to it, is that the work that we're doing is connected to the larger world. The work that we're doing is influencing the carbon emissions, is influencing the overall planet, whether we want it to or not. And then secondly, and we'll get into this a little bit more, but carbon efficient systems, if you focus on reducing carbon, and we're going to use electricity as a proxy to carbon in pretty much everything that we're going to talk about today, it'll make a system carbon efficient by reducing that carbon. Carbon efficient systems are faster, they're cheaper, and they're more resilient. Again, we'll kind of get into more of those details here in a little bit. So if you build software sustainably, not necessarily for sustainability, but in a sustainable manner, you can have a much better overall output, faster, cheaper, more resilient. And resiliency, that relates to hardware too, right? It's not just software. And so as SREs, we typically bring both the hardware knowledge and background as well as that experience in software to the table. And so, excuse me, a pretty commonly known thing in hardware is Moore's law, right? Number of transistors, they will roughly double every 2 years, and you'll get double the performance out of those. That's starting to slow. It's somewhat holding still, but it's starting to slow. A little bit less well known is a thing called Denard Scaling. And Denard Scaling says that, again, every 2 years, your performance per watt will double. And so we haven't met that since 2012. As of 2012, it's been done for almost 10 years now. In addition to these, our reliance on kind of various rare earth metals to create components, to create devices, we literally don't have enough materials in the world to meet our projected growth rates at our current rate that we're going at. There's just not enough in the world at all. And then, as processors get more and more dense with Moore's law, and that continues to go, they get hotter and they get harder to cool. And so we're starting to hit limits on the ability to cool some of this hardware as well. So kind of to recap here, we've got, double the material. We're doubling the material that we use roughly every 2 years. We're getting less performance per watt in that stuff that we're using. We're using rare earth metals to try and build these things, and it's a lot harder to keep all of this stuff cooler. Increased power and cooling demands, they just put further strains on our electrical grid and our cooling systems. We got to run more air conditioning to cool these things down, which then, emits more emissions out into the world, greenhouse gases, and then that causes it to get hotter, and then we need more cooling, and that causes it to get even hotter, which needs more cooling, and just keeps going and going. So when you think about it, if we don't have enough hardware necessary to meet demands, then we're pretty well tightly mapped to capacity planning on the Dickerson hierarchy here from the SRE book. And so if you don't have enough hardware, you can kind of go one of two ways. You can get more hardware, which, especially in this scenario, not really an option, or you can use the resources you have more efficiently. And so that balance of kind of efficiency with your job and what you need to do in the output and deliverables, that's essentially what SREs kind of are doing every single day in our roles. So, as a core function to SRE is that we're balancing these technical functionality capabilities in the system with the operational aspects, with the human toil that we need in order to maintain that system. And so the way that we typically will balance this is we use SLOs, right? And SLOs are this really great way to kind of balance this and show when toils become too much, or, we're not enough, and we can actually take a little bit out with some sort of budget that we've created through these SLOs. And so that balance that we're doing right there, that's reliability at the end of the day, is keeping that balance between these two layers of work. You can't obviously just do apt-get install for SRE because it's not just code at the end of the day. It's code, it's humans, it's process, it's culture, it's all these things that come together in a more holistic, systemic thinking. And so you have to design for reliability up front, and that has to be the central focus. Security and accessibility, they follow similar patterns as reliability, right? If you aren't designing for security up front and trying to bolt it on later, you don't really have a secure system. If you're trying to design for accessibility, or you're not designing for accessibility up front and you just bolt it on later, you don't really have an accessible system. And so SREs, at the end of the day, we're not really driving reliability. And that's because reliability is just a point in time measurement. What we really are driving is reliability over time, right? And so when you think about reliability over time, what does that really mean? Well, that means sustainability. And so at the end of the day, SREs are driving sustainability, and specifically the technical and the operational pieces that we talked about before, to create those sustainable practices across that entire system. So sustainability of the entire system is already the focus. Then we should be balancing technical and operational sustainability with the impact of the planet. And that's where environmental sustainability comes in. And so I'll just say up front, environmental sustainability is a huge problem. It has gigantic scope, right? And so here again, we want to focus this down to just carbon, right? We want to focus down to carbon and its proxies like electricity. You can find all different ways to kind of proxy your carbon emissions and carbon use by, energy efficiency. We already talked about. Resource utilization is another really good one. Storage saturation is another really good one to look into. Hardware life cycles themselves, like how do you make your hardware last longer? About 70% or so of a machine's carbon output over the course of its life comes from manufacturing, shipping, installation, all those layers up until you turn it on. You've used about 70 to 80% of carbon, of the lifetime amount of carbon that machine's going to emit, and about 20% of it is the actual use of that machine. So making them last longer gets you a huge way on this problem. So it's not as far off from the scope of an SRE as you may think. And so even more so, if we go back to kind of the SRE book itself, in the intro section, right at the start of the book, it lists the things that SRE should be responsible for. And so I've bolded them here, but availability, latency, performance, efficiency, monitoring, capacity planning, they all map to environmental sustainability and the environmental sustainability scope. So for example, let's look at the SRE golden signals. I kind of wish this wasn't a video because, I thought that pun was great, but either way, I'm sure everybody's laughing in the Slack, or not, or groaning. I don't know, either way. So the first golden signal, we've got latency, errors, traffic, and saturation. So the first one, latency. When you have a low latent system, you're going to see less bottlenecks. Those bottlenecks will kind of have less overall wait times. So you'll reduce your wait times. When as a metric here, when you turn them on, you use about 50% of their overall power just to have them on, not running anything at all. And then from there, you kind of use the rest of 50%. So if you don't even have a machine on, you're going to save a ton of your energy use right there. On the error side, low error rate systems, they'll have less retries overall because errors will typically trigger retries, so there's less traffic. Overall, you'll reduce the amount of processing and resource requirements in your system. For high traffic systems, that means if you can support a high traffic system, it means you are maximizing your utilization. It means you're typically maximizing your code efficiency. It also means you're maximizing typically your scaling efficiencies and how well you can scale up and down. That increases your overall resistance too. And then in a right size saturation system, I'm saying right sized here because it's very specific to how your system is set up, but you've optimized your utilization, you're minimizing your buffer sizes or how much extra capacity that you need to keep on in order to support these scale points. And you're also overall speeding up your requests when you have your right size saturation because, think of a database, for example. If you don't have to scan millions of rows because you're properly sharded, then that's going to be a much faster request. You won't have as much wait times up the stack and you can start to respond much more quickly. So interestingly, CPU performance per watt seems to balance out for most processors at about 70%. And I'll give a quick shout out to one of my colleagues, Bobby Mann, who did a lot of this work and putting this together. But for an i7 processor, looking kind of specifically at an i7 processor here, it takes a disproportionate amount of power as you approach kind of the maximum frequency of that CPU. So looking at the numbers here, you can kind of get right about that 70% mark is where the slope of the line starts to go a little bit higher, above linear. And so to go from, let's say, 3.5 gigahertz to 5 gigahertz in this chart here, you're going to get about 40% more output, more clock speed, right, out of your CPU there. But that same effort to go from 3.5 to 5 gigahertz is going to create 250% of the power just to get up to that point. And so again, that optimal point, if you start to look at the graph, is right around 70%. Now, every processor is a little different, and you'll probably have to do different analysis on these different ones, but this generally holds true, is right there. So you don't want to be maxing out your CPU if you care about energy efficiency. You also don't want to be maxing out your CPU if you care about the lifetime of that CPU. And same holds for a lot of other systems and hardware pieces in the stack. So why, this is great, this is awesome data, but why should SREs care? Well, to kind of go back over this a little bit, we've got, SREs have a holistic systems thinking. It's already part of the job. It's what we should be doing. It's how to do our job well, we have to be thinking of the full system. Carbon aware optimizations and carbon efficiencies actually improve a system and their bottom line. It makes it faster, makes it more resilient. Our planet is literally running out of materials to create these things. We will be getting into a capacity crunch here. We need to start consuming less resources to do the same amount of jobs, or more jobs, actually. It aligns to the golden signals. The environmental sustainability is embedded in those metrics, but really they align to just good engineering practices. You do more with less in general. You try to be efficient in your code. You don't want to waste cycles. It's just good engineering hygiene. And then finally, sustainability, it's reliability over time. So they're all matched up and they're all together. So now that I'm sure I have thoroughly convinced you that this is important for SREs and we should focus on this, how do we structure the type of work that would come through here? Is there a framework? And luckily, yes, there is. There are the principles of sustainable software engineering. And so these are 8 principles that have been defined, and they're all on GitHub, and they're open sourced. And so you can contribute to them. You can provide your own examples. You can help update these, add more. But essentially, it's a formalized effort. It's not part of a company or anything like that. It's a group of people that have started this. It's probably an entire talk on its own to go through these in detail, but I'm going to try and hit them real quick, and then we'll dive into some examples after that. So the first one, build carbon efficient applications. That's kind of what we've been talking about already. Pretty self-explanatory. Similar but still different is building energy efficient applications. So energy efficient is focused specifically on the power, whereas carbon takes a bunch of other things into account. You want to maximize the utilization for your system entirely. A great approach on this side is serverless, right? Serverless architectures allow you to use exactly the amount of compute that you need to use to do an operation. And so if you're looking to maximize utilization, you can start shifting towards serverless operations. Carbon intensity. So carbon intensity is the amount of carbon emitted in order to generate a kilowatt of energy or of power. And so when we say minimize carbon intensity, it means that we want to minimize the amount of carbon that we're producing in order to use that kilowatt of power. And we'll touch on that in a little bit. Embodied carbon is what I was referencing with the hardware, where it's the amount of carbon that's gone into that server, let's say, or that phone. It includes the manufacturing, it includes the extraction of the materials, it includes any production, it includes the shipping, it includes the packaging, everything that's gone into that thing that you have, or that device, that laptop. There's embodied carbon in there that's separate from the emissions that will generate from then on. Number 6 is minimizing the data amount and the distance it needs to travel. So how can you move things closer together? If you have a microservices architecture, for example, and you've got 100 different microservices, do you need 100 different ones to have to communicate through all those different paths? Can you put two that are maybe some tightly coupled or tight dependencies on the same VM at least, so that there's not as much distance to travel? Do you need to be pushing all of that data across the network, or can you use a different type of serialization software, or use something like protobufs to minimize the amount of data that needs to change or needs to travel across that network? Shaping demand to supply is an interesting approach where you can actually adjust what you're doing based on what's available. So if you are in a time of day where it's very sunny and your carbon intensity is low, you can offer more options. You can offer more features to your customers, as opposed to, when maybe it's backed mostly by coal. And so you have to start pulling features back because it's a higher carbon intensity. You see this already in some applications and products that, when they're under high load, they'll start to turn features off or turn services off to help save their resources underneath. And so it's a very, very similar approach there. Load shedding, Netflix is pretty good about doing load shedding and that type of stuff. That would all fall under this space. And then the last one is that end-to-end optimization of carbon efficiency. So not just your system, but all the upstream and downstream dependencies that can come into it and affect it, optimizing that path across there. So these are kind of the 8 principles of sustainable software engineering. Some of these principles map to fairly trivial changes that you can make. For example, look at CPU power itself for a specific kind. So AMD and Intel, there's vast differences between those chipsets. In general, again, an ARM-based processor is going to have less power draw to do its system. So if you're using VMs in public clouds, you can just look for specific chipsets if you want, and that can right there just reduce your level of carbon intensity and carbon emissions. Sometimes changes can require very little or no code at all too, even if they're not just fairly trivial. So one great example is there's a service called WattTime, and WattTime, as you see on the screen here, it's a map of carbon intensity really across the world, but I'm focusing just on the United States here. And then again, just to maybe dive into carbon intensity a little bit more, it's the amount of carbon required to produce a kilowatt of energy. And so when you think of solar or wind power, those take very little carbon or produce very little carbon to generate that energy. They just take the sun, they can convert it, and then they go. There's some embodied carbon in that, but it's pretty minimal, especially to generate over time. That gets amortized and you're fine. But when it's not sunny out or it's not windy and the turbines aren't turning, energy grids need to offset that with some other form of energy. And so typically that's going to be coal, that's going to be natural gas, it's going to be nuclear, some hydros in there as well. And so these energy grids will start to shift these things over time, and you see these fluctuations in the grid. You can kind of see it displayed here on the map, but this is more of a function of grids that have more renewable energy as part of them. But they're constantly changing, and new energy sources are coming in, and some are being decommissioned. So these things change over time, and they fluctuate based on weather, essentially. There's APIs available for this. You can pull this data and integrate it into your systems. And so an easy thing to do would be to understand where your data centers and where your regions are, and start to move machines to greener regions. There are in general, the West Coast of the United States has more solar, has more hydropower, which is a lot greener and more renewable, than the East Coast, which is a lot more, in general, coal or maybe nuclear. And so just in general, moving machines to the West Coast will help in your carbon intensity. One of my favorite little anecdotes is in Azure. We have 2 regions, one called US East and US East 2. Way more. We have about 50 or 60 regions, but there are 2 regions called US East and US East 2. They're in the same state. They're both in Virginia. But because of the way that the energy grids are on, they're both part of separate energy grids, different energy grids. And so US East 2 actually has more offshore wind as part of its energy grid. And so it is generally less carbon intense because of that offshore wind. So literally just by adding a little 2 into your config files to deploy to US East 2 instead of US East for Azure, you can drop your carbon intensity and drop your overall footprint of your application. There's also a good hackathon work that's been done for modifying a Kubernetes scheduler so that it can automatically read these APIs and select new node locations based on current carbon intensities. So it can put it in different regions based on the carbon intensities. And again, all of this API as well, they do forecasting and they do predictive analysis, looking at weather patterns. And so you could very easily dynamically look and start to pull regions away as these carbon intensities get higher and higher, and you can start to spin machines down and bring pods and nodes up in other regions that are maybe less carbon intense at the time if they get too high. Any machine that you're always leaving on is always just deployed. This is a really good option to just very easily drop it into another region and move forward. But say you can't just move machines around, right? You can still take advantage of the carbon intensity. By, instead of shifting things in space, you're going to start shifting it in time. So as I said, these things kind of go up and down. They fluctuate in time. This is a graph from California, one of California's energy grids, using a different API called Electricity Map, which is very similar to watt time. And you can see, during the day, the sun comes up and all the solar panels kick on. And so the carbon intensity drops during that day period. So if you ran, let's say you had a 1 hour batch job that you have to do and it just needs to be done at some point in the next 24 hours, doesn't really matter. Depending on when you run that 1 hour batch job during the day, you can save up to 40% of carbon intensity, just based on when you run it that day. Like I said before, watt time and electricity map, they both do forecasting. So imagine if you were maybe kicking off a build job or you had, a batch job like this. You could make a query before you do to understand what the next 10, 15, maybe 30 minutes are, and then delay that job as necessary to then get into a better scenario for carbon intensity and just do a quick calculation right at the start there to adjust or delay or pause some of these things. So just having this data available to you is super powerful and can save a lot of money, first of all, but also a lot of carbon emissions as well. So speaking of money, let's take a look at this Quantcast example, where they've saved millions of dollars and power and embodied carbon and carbon emissions by just switching up their Java serializer. So, as I'm sure many of you are aware, serialization can cause like some significant impact to processing speeds in a system, especially if you're doing it a lot and if you're using Java and reflection. So Quantcast, switched from a proprietary Java serializer to row files. And so in doing that, they ended up saving about 30% in their overall processing. You can see the cliff there. They run all their machines on their own, but they did the math and they said the equivalent of this in EC2 dollars, if you will, that 30% reduction would have saved them about $1 million in what they're doing. And so that's huge. And it also reduces their resource usage. It also reduces increases their utilization in the machines they're running. And so in addition to that, they also saved about a petabyte of storage because of the way that they were doing things. And so again, they run it all locally, but they converted it to EC2 dollars, and it's about $2 million that they saved just on the storage alone. And so, and they're reducing their resource usage again, even more. So there's opportunities everywhere once you start measuring and then evaluating the data. So let's do one more example here. So let's say in this theoretical example here that there is an industry that mines some resource and then they go and they refine it, right? And then they turn around and they sell it for a ton of money. And then that whole process is significantly hurting the environment. And so if this was in a room and not recorded, people would say, oh, it's oil or fossil fuels. And I say, no, it's not oil. Although it is kind of oil, yes, but it's not actually oil that I'm talking about. It's AI. It's artificial intelligence. So computation costs for AI have been doubling every few months, and they've actually increased over 300,000x in 6 years. That's a lot. And so it's a ton of emissions, and I'm going to try and put that in perspective a little bit for you here and say, let's look at some kind of benchmarks here for carbon footprints. And if we took a round trip flight from New York to San Francisco, that would end up being about 1,984 pounds of CO2 equivalent. All right. A human over the course of a year, just a person in the world on average, it would be roughly 5 times what that flight is. And then, just because we want to. Americans, we're a little bit more wasteful, we'll call it. We have a bigger footprint, and so we're roughly 3 times the global average. A car in the US over its entire lifetime is going to be about 126,000 pounds of CO2 equivalent. And then here's the big one. So a single AI model, so a 213 million parameter NLP model, that's going to be about 626,000 pounds of CO2 equivalent to run that model, that AI model. It's about 5 lifetimes of cars. Or another way to think of it is flying New York to San Francisco and back every day for almost a year. It's a huge number for AI. Now, there's efforts already underway. So green AI is one of the biggest ones, I would say. It's focused on this problem specifically, right? And the goal is really just trying to be transparent about the costs and costs to the planet itself too. So there's some efforts, but there's a long way to go. And then kind of to just really, drive the AI part home a little bit, let's talk about pigeons. So pigeons share a lot of the same visual system properties as humans in the way that they see. And so what they're doing is this pigeon in a box here with a little screen in front of him, or her, is training to detect cancer cells in medical images, right? And so they've actually achieved about 99% accuracy across the flock of pigeons in this scenario, whereas some most common AI algorithms in this image detection stuff would be around 90% accuracy. And so it's wow. There's a whole research paper that's linked here too, and you can imagine how much more efficient and how much less carbon is being emitted by the birds in this scenario, as opposed, especially in comparison to that AI model that we were showing before. So and as a side note, there's quite a bit of pigeon and tech crossover. It's fascinating. I definitely don't have time to get into today, but I recommend that you go look up all the various things that pigeons have done to either replace or augment tech here. So anyway, using kind of these green principles that we just talked about, and maybe some pigeons too, who knows, can actually help frame the environmental sustainability work that SREs should and could do. So if we look at kind of the 6 SRE responsibilities from earlier, from the intro of the book, and we take these kind of 8 sustainable software principles, what if we map them across? If we start to connect and trying to see, well, which ones are related to the others and how do they map? You see a ton of connection here. And there's really strong correlations at nearly every level in how tightly coupled SRE and sustainable software principles are. I really love kind of the web type visual here because it really just points back to how our work is interconnected to the larger impact and why systems thinking is just so important to what we do in our roles. So again, to kind of reiterate here, carbon efficiency or carbon aware systems, focusing on carbon efficiency brings many benefits to SRE and to our roles. So, first of all, saves money. This is a business. We all work for somebody or something, and it's something that's easily quantified. It's sometimes tricky to show the value of SRE in an organization. This is a very easy dollar amount to, this is the number of resources we have saved to bring this down. We're now maximizing our utilization. We're doing efficiency. These things kind of translate really well. It reduces complexity. You're simplifying your system. You're reducing the number of machines you have. You're reducing the amount of data that's getting transferred. You have to serialize. All that complexity comes down. You're also reducing the overall resources that you're required to use. And so you're becoming a more resilient, and you're becoming more efficient in what you have. You don't need as much stuff. You're doing more with less. You're practicing good engineering. And all of this increases your performance. When you're looking for optimizations everywhere, you're driving that performance up. Every one of these things that's listed here leads to increased reliability of your system overall. And so focusing on carbon efficiency gets you to reliability. And so that's why it really should be part of what we do. So again, just in case I kind of distracted you with pigeons a little bit earlier, let's look back at maybe some of the bigger takeaways. Let's zoom out a little bit here. So the first takeaway here is everyone has a part to play, but especially SREs. So when we talk about the environment, the planet, sustainability, efficiency, resource utilization, everyone kind of plays a part in that. But SREs are at that very critical point where we have probably the maximum influence over any other discipline that's out there right now. The other big one is set sustainability SLOs. Use power, use utilization, use carbon intensity as essentially proxies to carbon. And all of these, you can set sustainability SLOs by marking where you want your system utilization to be at, marking where you don't want to exceed a certain amount of power, you want to stay below a certain amount of power draw, where your carbon intensity numbers are and how to bring those down. Thirdly, SRE principles align with green principles. And so we're all in this together, but this is a very tight coupling. They're very related, highly dependent on each other. And the last thing I want to say as a takeaway here is, like, share your stories. This is kind of a sort of new field. It's up and coming. It's becoming a discipline. It's becoming more of a focus. And the more people doing stuff, the better. The more we can, use tools that others have created for our benefit, even better. When you can contribute back, keep that open source environment going. I especially like to hear about failures because that's where you learn the most. So don't hesitate to share failures either, not just wins. And if you want to do more, if you want to get involved even more than that, I always like to encourage people to read up on some of this stuff first. There's some really, really good posts in the SSE blog, the Sustainable Software Engineering blog. They're very good entries there about taking very practical approaches. There's code included in them. There's specific examples. There's implementations that people have done all within this blog, and there's tons of them in there. And so you can learn a lot very quickly in there. Also, another periodical from a group called Climate Action Tech, they put out, called Branch. A lot of the same thing. It's more in a like every 6 months or so format. And then it's not necessarily tech focused, but the heated newsletter is a really great place to learn as well for some of these things that are motivating. And then if you want to get involved, principles.green, open source, always looking for contributions there. Use your examples, add your information, add your data. Maybe we need new principles. Maybe there's some coverage that's gapped there. Join and contribute on that side. Climate Action Tech is one of the biggest, if not the biggest, community around sustainable software engineering and just taking action within technology around the climate. And then the Green Conf is a sustainable software engineering conference that's really great, and there's talks on YouTube for everybody that's gone through there. So there's many other things that I could point you to. So please reach out, and then I'll do my best to help. I'd love to hear any thoughts, pigeon project ideas even, or steps you're taking or want to take in this path. Please feel free to reach out to me. I want to thank USENIX again. Thank all the organizers at LISA and everyone involved to help make this happen today. It's really great to see, and then happy to continue to answer any questions that you have in the Slack chat or at any of these locations. So thank you very much. Bye.